Hello, this is the 7th video in our Conservation of Mass and Energy unit titled Conservation of Energy. The essential question for this is how and why does energy move around inside of systems? So there's two main terms we're going to be talking about here, energy transfer and energy transformation. As far as energy transfer, all energy can be traced back to the Big Bang. So we use energy transfer to talk about it going from one object to another, back, ever since the beginning of the universe. So for example, if you have a light turned on in your bedroom right now that's got EL, light is coming from the lamp, and that EL came from electrical energy that is located in the socket of your room. And that came from motion energy. We've got dams that create electrical energy from moving water. And that energy came from gravitational energy because the way the water got up in the dam, so because the water started above the dam and it turned into motion energy as it kind of plunged down through. And that gravitational energy came from thermal energy. The warm object that was creating that thermal energy got warm from sunlight, and that sunlight got its energy from the core of the sun, which got its energy originally from the gas that was pulled together to make the sun, and that gas got its energy from the Big Bang. So it's kind of amazing to think of every little thing around you, the sound you're making, the food you eat, every piece of energy can be traced back to the Big Bang. So the idea of energy transfers is how do we draw this trail, weave this story from now to the original motion, or the original energy, which was the Big Bang, because energy in the universe is conserved. So every energy everywhere now had to come from then. The other important word we're going to be using is a transformation. Transformation is similar to a transfer, except for it's within the same object. So energy can be turned from one type of energy into another, but stay in the object that it started in. So for example, this skydiver has gravitational energy when they jump out of the airplane, and then that gravitational energy turns into motion energy as they fall, but it's all staying within the skydiver. It's just turning from one type into another. Another example, this person in this, I forget what that's called, I looked that up at one point, but anyway, it sounds like a lot of fun. It's like a huge inflatable sphere that's on water, and they are going to be taking their chemical energy from the food they ate and turning it into rotational energy, amongst other things, as that ball spins. A really important note is that when you turn energy from one type into another in a transformation, or in a transfer really, usually some kind of energy is lost or wasted. Some common waste energies are sound or heat as things rub together. Doesn't mean those energies have disappeared, but they usually move away from your system and are not able to be tracked or kept in. So speaking of systems, how do we handle energy in systems? Well, the most important thing to realize is that the type of energy in the system is going to be changing over time through these transfers and transformations. So let's start with a little nursery rhyme. We got Jack and Jill up a hill fetching some water, and then they tumble down and crack their crowns, and the bucket comes tumbling after, or something of that nature. But what's happening to the energy in the system that is Jack and Jill? Well, at the beginning, before they go up the hill, I would say the primary energy that we would care about would be chemical, because that's the energy that's going to get them up the hill. There are probably a million other kinds of energy going on in their bodies, nuclear and wave and thermal, but those energies aren't necessarily the significant major ones that are changing. The one that's going to change, the one that's going to power this whole process of my story, is the chemical energy. So let's just give them 10,000 joules of chemical energy at the beginning. So now they're at the top of the hill. That energy's changed, right? They had to use that energy to climb up this hill. They now have primarily gravitational energy. They've gone up. They've moved away from the center of Earth. So maybe my system now has 8,000 joules of gravitational energy. Well, where is the rest of the energy? We started with 10,000. The answer is, as we climbed up the hill, some of that energy was wasted, right? The heat came off their body, they made noise, and so the rest of the energy, the other 2,000 joules, turned into waste as they went up the hill. Now Jack and Jill are going to fall down the hill, and that gravitational energy is going to turn to motion energy as they fall down the hill. They speed up as they go, but they don't get all 8,000 joules of it, because more waste energy and more thermal energy and more sound is coming off their bodies as they tumble down, and that is going to basically leave the system or move away from Jack and Jill, and they're going to be left with a less amount of the energy, the primary energy, which is motion energy. So you can see the story here, and hopefully you can identify the primary kinds of energy that each of these objects would have as they move through the story. But the question is, what kind of system is this? I don't know that there's a right answer to this. You probably could handle it either way. I think I would tend to call it I would tend to probably call it an open system because waste energy is hard to keep track of, but you certainly, if you knew how much waste you were generating, you could keep it closed as well. Is energy conserved? Well, hopefully the answer eventually is yes, because that's one of the primary principles of physics. But you can see how it might not look like energy was being conserved if you were only caring about these major types. So it's a little bit tricky. One tool that we'd like you to learn how to use in order to help keep track of energy in systems is called an energy bar chart. So for the same Jack and Jill system that we just talked about in the last slide, you should be able to graph using a bar chart the types of energy that are in existence in each of those moments in time. So at the beginning of the climb, we start off, and this orange bar is EC. You can see the key down there at the bottom. All 10,000 joules is energy. I put a really important bar on here, which is sigma energy. And the reason I put that on there will become clear really soon. It's the total energy in the system. Of course, in this case, it's 10,000 plus nothing, so it's pretty easy to add. But as I start adding some more complexity and start having more challenging systems, that total bar is going to be really important. So top of the hill, right, we have 8,000 joules of EG, gravitational energy. One note about that, gravitational energy means you've moved away from the center of Earth. It doesn't mean you can't be touching Earth. So you would have a lot of gravitational energy at the top of a mountain or top of the hill, even though you're touching the ground, because you're further from the center of Earth than you were at the bottom of the hill. So anyway, 8,000 joules of gravitational energy. I'm just making up these numbers. I didn't do calculations. And this is my waste energy, combined EW and ET. However, if you add up 8,000 and 2,000, hopefully you noticed already that my sigma in this case is still going to be 10,000 joules, so I haven't destroyed energy from the system of the universe. And then the last scenario, we've got tumbling down. In this case, we have motion energy here, and we have only 4,000 joules of it, but we have these waste energies that are, we have a little bit of gravitational energy. I guess I put me not all the way at the bottom of the hill, but the point here is that if you add up those three energies, it's going to add up again to 10,000 joules, which is my sigma energy. So in this analysis, I considered them as a closed system, and I kept track of all of those other kinds of energies that were generated. You could have done an energy bar chart with the same idea, the same story, with an open system, and then what you would have seen was sigma E going down, right? Energy leaving the system, it would have been going to a different system. But in this case, because sigma E was kept the same, we are basically considering this a closed system for this analysis. Okay, we made it through this video. Please revisit the essential question. How and why does energy move around in systems? What tools are we going to be using to track energy? What notes or questions might you have? This might be a presentation that you actually have quite a few questions on, so please use that extra space in your Cornell notes to put any questions down that you might want to follow up with me later on. Thanks for watching.